So in this lesson, we're going to look at atomic structure and have our first look at radioactive decay, which is something we'll cover in more detail in the A2. So let's start off with what makes up an atom. We'll then move on to isotopes and how we label atoms. Then we'll take a brief look at specific charge. Then we'll look at the strong nuclear force, follow that with radioactive decay, and then we'll finish with an exam-style question that should hopefully bring it all together. So let's start with the atom. Now the atom is made up of two things. It's made up of this, which is a positively charged nucleus, made up of nucleons, protons and neutrons, and then the rest of this structure, which is a cloud of negatively charged electrons. You may have before now seen the model of the atom being a nucleus surrounded by electrons orbiting around it, much like the Earth orbits around the Sun, the solar system model. Turns out that's not quite the right way to think about it, and this is better. A positively charged nucleus with a cloud of negatively charged electrons surrounding it. So now that we've identified the things in an atom, we have nucleons, protons and neutrons, and electrons. Let's talk a bit about their properties. So first of all, we'll start with the protons. Now, protons are positively charged. I'll just jot that down there. We'll talk about the absolute charge on these particles later, but we'll start off just by talking about their charge relative to a proton. So a proton's charge relative to itself is obviously just +1. Now it turns out actually that neutrons are neutral, as we can sort of see through their name. They have no charge. So the charge of a neutron relative to a proton is 0, but also relative to the absolute charge of a neutron is 0. And finally, we'll look at electrons. Now, electrons have, it turns out, the same magnitude of charge as a proton, just an opposite sign. So that means they have a charge of -1 relative to the proton. Now it's important to note that because they have the same charge as a proton, an atom, which is neutral, has the same number of electrons as it has protons. So now let's talk about its mass. Now a proton and a neutron, they have the same mass. They both have a mass of 1.67 times 10 to the minus 27 kilograms. A neutron has approximately the same mass as a proton. So writing this in the mass relative to a proton, we see that proton has a mass relative to itself as 1, and a neutron is approximately 1 as well. Now, this doesn't look like a lot, and it's not, but it turns out that actually this is most of the mass of an atom, because also atoms are very small and don't have a lot of mass at all either. So actually we can see this by writing down the mass of an electron. An electron has a mass of 9.11 times 10 to the minus 31 kilograms. That's about 3 or 4 orders of magnitude smaller than a proton or neutron, and so almost all of the mass of an atom is inside the nucleus, made up of the protons and neutrons. We can see that very easily by writing down that the mass of an electron relative to a proton is about 0.0005. It's very small. So now coming back to the absolute charge on a proton and an electron, we've just seen that they have an equal magnitude but opposite sign charge. And it turns out the actual absolute charges are, well, a proton has a charge of plus 1.60 times 10 to the minus 19 coulombs. Coulombs are the unit of charge. And so electrons have a charge of minus 1.60 times 10 to the minus 19 coulombs. Electrons negative, protons positive. It's important to note that if an atom gains or loses an electron, so it's no longer uncharged, it becomes an ion. An ion is the word we use to describe a charged particle, an atom that's lost or gained electrons. If it gains electrons, it becomes a negative ion. If it loses electrons, it becomes a positive ion. So now let's look at isotopes and how we actually label atoms. So each atom of an element, now what do I mean by an element? Well, it just means something we're very familiar with as it is. I could mean something like gold, which has the elemental symbol Au. I could mean oxygen, symbol O, carbon, which has the symbol C, or lead, which has the symbol Pb. Each atom of an element has the same number of protons, and we call this its proton number, the proton number of an atom, or atomic number, and we give the symbol Z. Let's look at some examples briefly using the elements we've just written down. So if this is our element, and this is our atomic number Z, we see that gold has an atomic number of 79, so there are 79 protons in a gold nucleus. Oxygen has an atomic number of 8. There are 8 protons in an oxygen nucleus. Carbon, 6. And lead, 82. And that's true for any carbon atom, any oxygen atom, etc. They all have that number of protons in the nucleus. But all we've talked about there are protons, and as we saw before in the atom, we saw that they could have protons and neutrons in a nucleus. So what about those nucleuses? It turns out that atoms of an element can have a different number of neutrons, and these are called isotopes. So what does that mean? Well, it means that different nuclei can be of the same element but have a different number of protons in them. And so this is our definition of isotopes. Isotopes are atoms that have the same number of protons and a different number of neutrons. We say that the total number of protons and neutrons in an atom is called the nucleon number, A, or occasionally the mass number. We call it the mass number because it is almost numerically equal to the mass of the atom in relative units, where the mass of a proton or neutron is approximately 1, as we talked about on the last page. Let's talk about how we actually label these isotopes. Let's say we have a random chemical element X. Now X could be anything. It could be oxygen O, it could be carbon C, it could be lead, it could be iron, it could be anything. We'll just go with X. We see that up here in the top left is we write A, and this is the, as we discussed above, excuse me, this is the nucleon number, not the atomic number. And then here at the bottom left we write Z, which is the atomic number. So let's do an example of this. We could have, well, there are two very common types of carbon. There's carbon 12 and there's carbon 14. This means that both have 6 protons in the nucleus, but a different number of nucleons. Let's say we wanted to find out how many neutrons an atom has in its nucleus. Well, what we do is we see that the nucleon number, you know that nucleons are just protons and neutrons, the nucleon number is just the proton number plus the neutron number. So number of neutrons, number of protons. So we see that the number of protons, the number of neutrons, which is what we want to find, is just equal to, well, the nucleon number, so the A, minus our proton number or atomic number, Z. So we can see that carbon 12 has 12 minus 6, which is 6 neutrons, and carbon 14 has 14 minus 6 equals 8 neutrons. And each type of nucleus is called a nuclide, and we label them using our isotope notation. Great. So now that we've covered how we label atoms, let's move on to specific charge. Now the specific charge of a charged particle is defined as its charge over its mass. So we take any charged particle, we divide the amount of charge it has by its mass, and that gives us a specific charge. So a charged particle with a lot of charge and not a lot of mass will have a high specific charge. A charged particle with not a lot of charge and a lot of mass will have a low specific charge. An example of this could be, let's just go with a hydrogen atom, a hydrogen nucleus. Now this is actually, hydrogen nucleus is important, an atom is uncharged. Hydrogen nucleus is actually just a proton. We can see that here because it has a nucleon number of 1 and an atomic number of 1. That just means it has 1 proton and 1 nucleon in total, so no neutrons. So it is literally just a proton. But then we know things about the proton. We know that the charge of a proton is 1.60 times 10 to the minus 19 coulombs. We know that its mass is just 1.67 times 10 to the minus 27 kilograms. So that means that the specific charge of hydrogen, of a hydrogen nucleus, or a proton, turns out to be, if we run it through a calculator, 9.58 times 10 to the 7 coulombs per kilogram. And we could do this with anything, and the actual calculation is less important. Like, you just take the charge on the particle and divide it by its mass. It's less important than noting what's going to give you a high or low specific charge. So if we have two, let's go back to carbon-12 and carbon-14, carbon-12, carbon-14, we see that if we have a charged carbon-14 ion and a charged carbon-12 ion, they're going to have different specific charges, even if they have the same charge in total. Let's say they had a positive charge of 1.60 times 10 to the minus 19 coulombs. They've lost an electron, but because the carbon-14 has a higher total number of nucleons, it means it has a higher mass. So we can actually see that given same charge, specific charge of carbon-14 that's less than the specific charge of carbon-12. So to find the specific charge of something, we simply take the total charge the particle has, and we just divide it by its total mass. And we can find the total mass very easily just by looking at the nucleon number it has. So we could do this for an electron, we could do this for just about anything. This video is starting to get a bit long, so I'm going to stop here and we'll come back to the strong nuclear force, radioactive decay, and then our exam style question in the next video.